Okay, this video lecture is for section 4.5, linear approximations and differentials. Really for this section, when we talk about linear approximations, that's really just a fancy term for finding the equation for this line. So in other words, if we have this function here in blue, and we want a linear approximation, we just really want a line that passes through a point of interest. So in this case, a point that passes through x equals a. And we want that line to represent the value of the function in this area around the function, where the line and the function are close in value. So, so we have this tangent line then that's a close approximation. Okay, if we tried to use the red line to approximate something out here, where my arrow is, the distance between the approximation, the red line, and the actual curve is so big that it wouldn't be a good approximation. But we can actually use this line to approximate the value of that function or that blue curve really close to it, where the distance between those two are not that great. And of course, if we can use a line to approximate a value for something more complicated, like something that has curves in it, then it makes the math a lot easier. So when we do that, we call that the linearization of the function. So if we look at linearizing a function, and again, that's just really a fancy term for finding the tangent line, which we've done already in chapter 3. If you want to linearize a function, we really have to start with the equation for a line. So here's our point slope equation. Here's our slope, x minus x1, that would be a in the other picture, and then y1 would be f of a. So if we substitute in those values, so we have a certain point, x equals a, and we have a certain function value, f of a. And then we have a slope here, which when I say slope, you think derivative. We can substitute those expressions into this point slope equation and get an equation that's that's nicer to use for calculus. So it looks something like this. So we have the equation for the line being y equals the derivative times x minus a plus f of a. And so we call that the linearization. So really all we do is we just change the y to L of x. So this literally is point slope form, term for term. We're just rewriting it and calling it the linearization because we're using this line to approximate a value. And so we say L of x is the standard linear approximation of the function at a. So it's approximately equal to the function value. It's close in value, but it's not exactly the value. And again, just a fancy name for finding the tangent line to a function. So we've done this in chapter 3. This is really nothing new here. We're just calling it a linearization. So if we find the linearization for a function of 1 plus the square root of x at 0. So we know a is 0, and we know then the value of the function at a, or so at 0 is 1 plus 0, and take the square root of that, which is just 1. And then we have to take the derivative of this. So thinking about square root of 1 plus x, that's really 1 plus x to the half power. So we bring down the half and then times 1 plus x to the negative half. So this is already rearranged. And so our derivative at 0, plugging in 0 for x, is a half. So we have our derivative, which is our slope. We have our a location, which is 0, and we have the value of the function at a, which is 1. So we can go ahead and put in our slope, our a value, and our f of a value. So this is the linearization of that function, which is a curve. If we simplify that, we can just write it like that in slope-intercept form. The next topic is something called differentials. So differentials is that dy or that dx, okay? And differentials came about when we started talking about the change in y and the change in x. So how those are changing as we move about the curve. And when that change becomes really, really small, then we use the differential d instead of delta in those expressions. So really when we talk about dy, we're just really talking about a really small delta y. And dx, we're talking about a really small delta x. So, so we can use dy for a small change in y, for a small delta y, and we can use dx for a small delta x. Let's try this one. Let y equal a differentiable function, f of x, and the differential then dx is the independent variable. So think about y equals f of x, right? X is the independent variable, and then y depends upon the value of x. So the differential dy is just the derivative times dx. So if you think about the expression dy dx being another expression for the derivative, we're really just moving the differential dx from the denominator on this side under the dy over to the right side of the equation. So to find the differential for this, we take the derivative, so 5x to the 4th plus 37, and then we, in a sense, we can just say multiply both sides by dx, but what we're doing is we're reassigning the differential to the other side. And so here's the differential dy for that function. In this example, we can use that to get the change in a value. And so we're going to use the expression for a differential to see how much the area will change if we change the radius by 1/10. So we know that the area of a circle is pi r squared. And we're going to take the derivative of the area with respect to x. So we do a chain rule here because we're taking the derivative with respect to a variable that's not occurring in the expression. So dA dx is 2 pi r, right? This is the chain rule where we're taking the derivative of r squared, we're getting 2r, and then we have to do dr dx to get back into, to get this derivative with respect to x. However, if we look at that expression, really we have a dx in the denominator on both sides. And so we really end up having dA equals 2 pi dr. In other words, we could have just done a dA dr on this original equation and moved the dr to the other side, like in the previous screen. So this is the very small change in the area, and we can find the very small change in the area if we know the small change in the radius. So to find that small change in the area, we have 2 times pi times the radius, which is 10, times the change in the radius, which is 0.1. So if we, 10 and 1/10 are reciprocals of each other. So our small change in our area is 2 pi. And that's an approximation. That's not an actual value. So this is the approximate change in area. If we look at the actual change in area, we know that the new area is pi times 10.1 squared, because if we have a change of 1/10 in our radius, our new radius is 10.1. And so there's our new area. Our old area is pi times 10 squared. And so our actual change here is 2.01 pi. So our actual change is just a little bit bigger than our differential. So again, this differential, it is an approximation. Just like that linear approximation is an approximation. Okay, so there's a difference of 1/10 pi. This is a small difference because again, if we take a look at what we're looking at here, we're looking at 10.1, a radius of 10.1, which is really close in value to 10. So we're looking at using that differential to approximate that change in a location that's really close to where we started. There we go. Almost skipped a screen here. So if we combine these two ideas, this linearization idea of the linearization, and again, this is just a point slope form. This is y equals mx minus x1 plus y1. So we take this concept of linearization and we take this concept of differentials. We can see that this differential expression is really f prime dx. That's the derivative or the slope. Dx is the change in x. So here's our slope and our change in x. And our dy is our change in y. So if we think about that, our change in y is going to be our final minus our initial value. So if we bring this to the other side, we have, and we're going to put back the function notation and take out the linear notation. We have f of x minus f of a. So that's bringing f of a over to the left again, equals f prime of x, the derivative or the slope, times dx, which is the differential of x, which is the change, which is, keep changing the screen there, which is the change in x, which is this in the parentheses. So, so if we look at that, then we can see that when we bring the f of a to the right side, we get back what we started here. So the differential expression and the linearization expression are really the same thing, with the f of a taken to the left side to get our differential with respect to y. When we talk about graphical representations here of linear approximations, the linearization, we can use that to approximate the value of a function in close proximity to where it is tangent to the curve. So in this case, we are going to use our linearization to approximate the value close to x equals 5. Okay, so we want to approximate the value of 4.9. So if we want to approximate the value of 4.9, we're going to take an a value of 5, and that gives us our function value of 4, and our derivative at a is not, we now have to find our derivative at a, and we can do that, if you notice, we do that by just a old school slope method, right? When I say derivative, you think slope. And when we look at this blue line, since this is a graphical method, we have to get our information from the graph. We see that the blue tangent line goes through 0.54, and then if we follow the tangent line down, it also crosses through 1, 0. So that being the case, then our rise is 4 minus 0. Our run is also 4, 5 minus 1. Those are the y coordinates and the x coordinates. So our slope is 1. So we're literally getting that information from the graph. And to find that slope, we know the blue line is a tangent line. So as long as it goes, we can find a point there that it goes through that's convenient, we can find the slope or the derivative. So now we can go ahead and set up the approximation. The differential, I forgot about the differential. The differential here, what we're talking about, the dx, is we're approximating at 4.9. So we have to take our x value, which is 5, minus our our x value, which is 4.9, which is where we want to find our approximate, minus our a value, which is 5. So our dx is 1/10, and it's negative. So if you think about it, if here's our a value, this is where we're tangent to the function at x equals 5. We want to approximate at the value at 4.9. We're stepping backwards in the graph at 4.9. So our dx is negative because we're stepping back. We're stepping to the left. of where of that point of tangency. So since we're stepping to the left, our dx is negative. So putting that into the expression here at the top of the page, our approximation at 4.9 equals our slope times our differential plus our original y value of 4. So after we do the math here, that's negative 0.1 plus 4, that's 3.9. So we're approximating the value, the function value at 3.9 using this graph. So if we really zoomed in here, if this is x equals 5, and maybe this is about this location is x equals 4.9, then we can see that there's just a tiny gap between the linear approximation, the blue line, and the black curve. So that just that little bit of difference is, we're seeing that that linear approximation, that blue line, its value is about 3.9. Its value is a little bit bigger than the actual function because it's above the function. Now let's go ahead and approximate something on the right-hand side of 5. So we're going to try to approximate the value of the function at 5.04. So again, we have this point of tangency at an x value of 5 and a y value of 4. So we know our a value is 5 and our function value is 4. And our derivative is the same as it was before. We're using this point 5 comma 4 and this point 1 comma 0 to come up with a slope. And that slope is the derivative of that line because it's a line. So the algebraic slope and the derivative end up being the same number. So our differential now is our x value, so our 5.04 minus our a value, which is our 5. So in this case, our point of tangency is x equals 5. We're estimating out here at 5.04. So we're estimating to the right of our point of tangency. So our dx is a positive number, positive 0.04. So substituting that in then, the approximation at 4.9, so that's what this is here, that linear approximation, equals 1 times the differential, 0.04, plus the function value, which is 4. So working that out, we get an approximation of 4.04. So looking at it this way, if here is x equals 5, and we're out here at 5.04, then we, if we use the linear approximation, that value is 4.04, which means we're traveling along this blue line because that's the approximation line. And if we notice that that blue line is just a tiny bit above the curve, so this approximation is just a little bit bigger than the actual value. So here's another example. We're given the graph of the function, and this graph is the function of the derivative, or the value of the derivative, excuse me, I should have said that better. It's not the function, it's the actual derivative value. So if this is the actual derivative value, then if this is the actual derivative value, then at x equals 3, the derivative is 3. The information this is giving you is the derivative expression right here. So we're going to approximate at 2.94. We want to find the linear approximation at 2.94, which is just under 3 here. So we're going to have this linear approximation line that's going to be tangent and to the curve here. And we know we have an a value of 3 and a derivative value of 3. But then that's not the function value. The function value is actually given in the problem. The value of the function at 3 is 6. It's the derivative value that's actually 3. So we don't really need a tangent line drawn here because we get the derivative value right from the graph, since we are graphing the derivative. the increment then is x minus a. So since we're approximating to the left of a at a slightly smaller value than 3, this is going to be 2.94 minus 3. It's going to be negative because our approximation is to the left of the value a. So our differential is negative 0.06. So looking at then and putting that into the linear approximation expression, we have the estimate at the approximation at 4.9 equals the slope, which is 3, times the increment, which is negative 0.06, plus the initial y value of 6, which is not represented in this graph alone at anywhere. We get that value from the statement here. And so simplifying this and coming up with an answer, we've got negative 0.18 plus 6, which means our approximation at 4.9 is 5.82. When we take a look at, let's try approximating a little bit larger at 3.1. So we're now approximating on the right-hand side of 3. Our a value is 3. This is where we have our point of tangency. Again, our function value at 3 is 6 from the problem statement. Our derivative is still 3. We're going to get that from the graph. And our increment now, we're approximating 3.1, so we're over here to the right of this point of tangency, which means we're going to have a positive differential. So that's going to be 3.1 minus 3. So our differential is 0.1. And plugging that into the linear approximation expression to approximate the value, we have the linear approximation at 4.9 equals the derivative, which is 3, times the differential, which is 0.1 plus 6. So simplifying that, we have an approximation of 6.3. That's the approximation of the function at a value of 3.1, so just to the right of that tangent line, that point of tangency. So at this point, you should be able to do the linearization homework for section 4.5 in WebAssign.